Mhm.
Well, good afternoon, everyone. Thank you for coming to the Energy Symposium this afternoon. A couple of admin remarks. First off, for next week, next Thursday, we've got Dr. Charles Fosberg from MIT. He's going to come talk to us about coupling heat storage with nuclear reactors as a way of doing dispatchable and load following with nuclear reactors through stored energy in thermal applications. Same time, same place next week at 5:15. So again, if you're interested in that kind of topic, please join us. Today, we've got the honor of having Dr. Kevan Weaver with us. That a little shout out there, John? Or okay. Kevan is from TerraPower, where he's been at since 2007. He's the Director of Technology Integration there. But what I find compelling is he was with Idaho National Lab for what, you were there almost a decade, weren't you?
Yeah.
At INL. And researching in nuclear reactor concepts. His bachelor's degree is from the Brigham Young University, and he did his PhD in nuclear engineering at the University of Utah. I first met him this summer at a conference on nuclear power in DC, and he gave a fantastic presentation on Gen 4 nuclear reactors that I found very compelling. There's not just one of them out there. There's maybe 5 or 6 different competing technologies in the Gen 4 reactor world. So when we talk about the potential for SMRs, small modular reactors, that's a fairly generic term. There are several competing technologies that could be used in SMR applications. Tonight he's going to take about 45, 50 minutes, walk us through what some of these different competing Gen 4 technologies are and the potential options in SMRs. We're going to reserve 15 minutes at least for questions following up, and please do. He wants to hear your questions. He wants to know what you're interested in or concerned about, and not just the technology aspects, but the business, the economics, the political aspects of where we are with nuclear in the United States, where we may or may not go in the future, as well as what happens internationally. Following our talk, we're going to go over to Gabriel's Bar at the AT&T Center. I shouldn't say bar. I should say lounge, right? We'll go over to Gabriel's at AT&T, and if any of you would like to join us to continue the discussion, we can have some adult or non-adult beverages and some food and continue the talk. So again, thank you all for coming, and Kevan, it's yours.
Thanks, Fred. Don't clap, at least not yet, and you might not want to at the end anyway. So, thanks for inviting me to give a talk. This is based off, actually, as Fred said, that a discussion that we had in Washington, D.C. earlier this year. So I essentially took those slides and went through them. But the fortunate thing is, though, is that just as a little bit more background, as far as the Generation 4 reactors or nuclear energy systems are concerned, I was fortunate enough that when I went to the Idaho National Lab, that was my first job out of grad school, I was involved in them from the very beginning, which is really nice. So that was the 1998. In fact, Gen 4 really didn't officially start, meaning sign off on it, until about 2002. So from about 1998 until that point, we were gathering people together, getting international folks together, and I was involved pretty heavily in all that. So it worked out really well, and it was good timing on my part with regard to my career. So what I'm going to do then is I'm going to talk about the systems that were talked about and then were essentially put forward as the ones that would be the Generation 4 systems. And one thing I do want to say is that when you look at them, you realize that with the exception of maybe only 1 or 2, there is some previous technology that they were based off of. I think the difference is between the modeling capabilities, meaning computational capability, that we have now, and specifically the materials that we've developed since then make them much more viable, at least in our opinion. So let me jump right into it. So the first 3 slides, I'm going to talk a little bit about the motivation. So this is not necessarily the motivation that we had in Gen 4. That will come on about slide 4, and we talk about the different things that we are looking at. But from the standpoint of TerraPower, this is what motivated us. And of course, we then adopted one of those Gen 4 technologies. Actually, we've adopted 2 of them. And I don't have slides on those, but I will discuss them as I discuss the different technologies. So The first one is that we have a lot of people in the world. There's going to be a lot more that are going to come into the world. And the idea is that if you want to keep their standard of living or bring their standard of living up, how do you do that? And this actually ties into the chair of our company, Bill Gates, and some of the efforts that he and his wife have been working on, which is, of course, poverty, disease, things like that. And it turns out that when you look at especially poverty and disease, that there's a one-to-one correlation between that and energy use. The higher the energy use, the better off you are. That's essentially what it is. And it turns out on the disease side, a lot of the medicines that they want to use for the diseases need to be refrigerated. So you have to cool them somehow. And you need then electricity or availability of electricity to do that. So as you go through these, and this is primary energy use, and the real question is the bullet on the bottom. So if we want to bring the rest of the world up to a certain standard of living, how much is it going to take? And it turns 3 to 6 times basically what we have now. So we're talking, and you see that second to the last major bullet, that's about 100 terawatts of energy. And the reason I bring that up is because it's a scaling problem. We talk a lot about different energy sources, and I'm not going to argue for or against one or the other, but when you look at what you're going to need between now and then, there's a huge scaling problem here, and we've got to fix that. And it turns out, of course, because of my background and what our company's doing, we feel that nuclear can be part of the solution to that problem and that challenge. All right, this is just illustrating that on the side of energy, primary energy use, if you look at the pie, you've got about that cut into about thirds: electricity, transportation, and industrial uses. On the electricity side, the expectation is it'll double by 2040, meaning the need for electricity will double. And if you start talking about electric vehicles, that goes up even farther, right? So that means electricity starts to there's an incursion of electricity into the transportation sector. That could go up even more. And when I say the future is global, what I mean to say is that if you look at countries that are developed, if you look at their energy growth, it's in the single digits right now. And it's because we've gone up this curve very steeply, and now we're sort of at this asymptote. And most of the industrialized countries look like that, meaning at that asymptote. The problem is that there's a big portion of the world's population that is not on that side, a very big, and that's the part where you're going to see a lot of growth. So the growth is actually global, and then we can talk about that on the question side later. All right, so now I'm going to jump into the advanced reactors, specifically the Generation 4 reactors. So I said this a little earlier, with the advancement of materials and computational capabilities, we feel like we can take them the next step from where they were before. And so there's 4 basic areas that they've looked at, including water-cooled, but it's very different. And it'll be illustrated when I get to that slide. So there's liquid metal-cooled reactors, there are gas-cooled reactors, there's molten salt, and that molten salt means it could either be cooled by a molten salt as a solid fuel form, or the fuel could actually be dissolved in the salt, and the salt is the fuel is liquid and actually moves throughout the core. And so these Generation 4 technologies, as I said before, most are not cooled by water, but almost all of them operate at much higher temperatures than current reactors. So think of it this way. I think the current light water reactor fleet between boiling water reactors, I'll try not to use too many acronyms because I'm not sure what the constituency in the audience is, but boiling water reactors and pressurized water reactors, their outlet temperatures are roughly below 300 degrees Celsius, anywhere between 250 and 290, roughly speaking. And these reactors we're going to talk about, most of them operate above 500 degrees Celsius. So what that offers is, of course, a pretty big leap in efficiency. It's just, you look at, Carnot cycle, just do the calculation. You can get a pretty big bump in efficiency just by getting the temperature up. But the other thing, which actually impacts the safety of these, is that most of these systems, or I shouldn't say most, at least half of these systems aren't pressurized. So right now, to get the water temperature up above boiling without it boiling, you pressurize the system. The problem with that is now there's a driving force, so if you actually poke a hole somewhere, all your coolant gets squirted out, right? That's a problem. If you keep it at atmosphere and you design it right, there's no motive force to push anything out because there's no pressure, right? So you have a safety advantage. And I'll talk a little bit about those as I go through some of these reactors. So there are 6 systems, and you can see those on your right. But I want to start on this side here and how we get to that over there. So you have the early prototypes. You go from there to the large-scale plants that were built. Then you go to what has been termed evolutionary design. So these are the Gen 3 and 3 plus. So this is like the AP1000 from Westinghouse, the EPR from Areva, the ESBWR from General Electric, and et cetera, and includes also the small modular reactors. Keep in mind, though, that in this set right here where it says evolutionary designs, these are almost exclusively water-cooled, including the SMRs. So NuScale has an SMR. Mitsubishi's done an SMR design. In fact, all the big nuclear companies have some sort of small modular reactor design. But almost without exception, they're all water-cooled. So seriously, one of the big differentiating factors between Gen 3 and then Gen 4 is that the majority of the Gen 4 ones are not water-cooled. And let me take you to those as soon as I get past this one. Sorry, I'm trying to remember where some of these slides got placed because I moved them around a little bit since last time. So when I said at the beginning, there's motivating factors for TerraPower and pursuing a Generation 4 reactor, but overall, when you go back to the beginning of the Generation 4 and Generation 4 reactors, there were really these four things that were being considered. One is sustainability, the other one was safety and reliability, the third one was economics, and the last one was proliferation resistance. And the idea is to take them from the technologies where they are now and better them in all of these areas. And some reactors do a little better in some of the areas and not so good in some of the areas, and other reactors do better in the other ones and not so good in the previous ones. So there's a balance between all of these. Just to go back, just because I was involved in this, and in some sense it was a little painful, is when we look back and we came up with the 6 systems, of course there was a lot of debate and arguing going back and forth between all of the folks around the world. So these were the original, I think there were 10 countries. So it was the US, France, Japan, Russia, Brazil was even part of it. But certainly the countries that had current nuclear programs and had large commercial reactors they were designing, building, and running. But we stepped back and we looked at them. The thing that was interesting was they looked at them, and the ones who had specific designs that actually fit the Gen 4 criteria, they would come forward with them and then say, this is the best. It covers all of these. But when you really sat down and took an honest look at them, depending on what reactor it was, depending on how well you did and how well you ranked in these here. And so as part of the process, what happened was we didn't decide on 6 reactors in the beginning. What we decided on was we were going to rank these, and then the ones that floated to the top, we'd either bin them or figure out some way to put them in groups, and then decide from there what were the 6 that all the countries that were in the Gen 4 International Forum were willing to say, these are the ones we're going to pursue. And we're going to pursue them internationally. So in some sense what happened was with the Gen 4 International Forum is that treaties, it was treaty level signatures that were happening in all of this. I think as we go on, you'll figure out the challenges were, and I hope questions come up afterwards about, well, where are we on these? That was back in 2002, and now we're almost 2018. But it's a difficult process. So just keep in mind that these were the criteria that were put forth in Gen 4, and then when those reactors are ranked, in the end, all the community, meaning those 10 players, and I think now it's 12 or 13, decided, yes, these are the ones we're going to follow because they exceed, at least in the opinions of the experts, exceed the current reactor designs in all these areas, meaning these light water reactors, and some exceed others, okay? All right. So, make sure I time this all right. The sodium-cooled fast reactor. So what you'll see, of course, is some words over here, a diagram over here, what it might look like, and then up in the corners of all these slides, you'll see a temperature range. So these are the ranges of outlet temperature. So this is the temperature that ends up getting to whatever the power conversion cycle is. In this case, it's a Rankine cycle. It could be something else too, by the way. So the reactors that you'll see here too, sorry, I need to back up at least one step, is you'll see that there are 3 that say fast reactors, and there's a 4th of the 6 that could be operated in fast reactor mode. So for those who don't know, a fast reactor means that this operates on a fission spectrum rather than a thermalized neutron spectrum. So when the neutrons are born in fission, their average energy is about 2 MeV. if you put that in water, those neutrons will bounce off the hydrogen atoms and be slowed down, and they get down to about 0.00650 eV. So there's several orders of magnitude in energy that's lost. That when you run these reactors, you don't lose that energy. So their physics is different. They behave different. They behave differently. And fortunately for the sodium fast reactors, as an example, we've built some of them around the world. So you can see up there, actually there's designs being developed, but what it doesn't show you, besides the BN600 and BN800, here in the United States, we built experimental breeder reactor 1, which was built out in the desert in Idaho. For anyone who gets out there, it's kind of out in the middle of nowhere, by the way. But if you get out there, it's a National Historic Monument. You can go out there, you can tour the facility, you can see where the reactor was in the control room. It was actually a sodium-cooled reactor and was the first reactor that produced electricity civilly, meaning from a civilian standpoint. So it was actually a sodium-cooled reactor, not a water-cooled reactor. But there's experimental breeder reactor 1 in the United States, experimental breeder reactor 2 in the US, which operated from the 50s, 60 time frame all the way up until about 1994. So it had a very long time frame. And then we built a third one. And so let me back up. Okay, so the three that I'm mentioning right now, these are all Department of Energy or used to be Atomic Energy Commission reactors. So the Fast Flux Test Facility was built out in eastern Washington State at Hanford, and it was a much larger sodium-cooled fast reactor. There was one commercial sodium-cooled fast reactor built in the US, and that was Fermi 1. And it actually had a core meltdown. It had some blockage in one of the assemblies, couldn't get the coolant to flow through, and it melted part of the core. The difference, though, between what happened at Fermi 1 and what's happened with light water reactors is because it was sodium, it trapped most of the fission products, so there was, actually, we haven't had a release in the United States because of that. Chernobyl, different story, Russia. But the sodium-cooled reactors, it turns out if you do melt them, it's actually fairly easy to clean them up. You take them out, clean the coolant up, put a new core in, start over again. That's not the case. Light water reactors, we typically shut them down and they're decommissioned. So Fermi 1 had an accident, and so did EBR 1. They both had, yes?
So if we invented this for pioneer, why aren't there any U.S. companies pioneering design?
That's a great question, and the answer is if you look at that first sub-bullet, can either burn actinides or breed fissile material. The fast reactors were originally envisioned and built to take advantage of converting uranium to plutonium and then using it as fuel in a closed, what we call a closed fuel cycle, right? Well, we did that because we thought uranium resources were pretty scarce. So this is back in the 1950 time frame. As the nuclear era wore on, and the push really from the nuclear standpoint was really the Navy to build reactors in the beginning, and then those eventually turned into commercial reactors, we started finding more and more uranium. And in fact now, uranium is pretty ubiquitous. You can find it anywhere. You can find it in seawater, by the way. And in fact, not only can you find it in seawater, the Japanese have been working on membranes that you can drag through the ocean and pick up uranium, take it in, strip it off, and do it again. It's more expensive than mining it, where you have places where the uranium ore is very rich. But in the whole scheme of the cost, keep in mind that nuclear fuel is roughly 10% or less of the cost of the operation of the plant. So you can double the cost of your fuel, and it doesn't really do a whole heck of a lot to the cost of your electricity. So hopefully that answered your question. We didn't build them because we found out there was a lot more uranium. And when you do close the fuel cycle, you add cost to that. Even though I just said that the fuel only adds 10%, when you're competing on very thin margins and you're competing against other sources of energy, it turns out these, frankly, back then were not considered economic. But at the end of the talk, I'll talk about where we've taken this sodium fast reactor concept and turned it on its head and say, no, you don't have to reprocess. Cuts out that whole piece. And then can we then become competitive with current technology? So there are 2 commercial plants running right now. Those are in Russia, BN600 and BN800. And then India is about ready, probably within the next year and a half to 2 years, we'll start up their prototype fast breeder reactor, which is a commercial version. All right, lead-cooled fast reactor. So What you do with lead then, it looks a lot like the sodium plant in some sense, but the difference is instead of having liquid sodium as the primary coolant, you actually use lead or lead bismuth eutectic. And the advantage you get there is that sodium, especially in liquid form, is very reactive, highly reactive. You don't have to worry about that with the lead, but then with the lead, all these have trade-offs, by the way. As I go through, I'll try to talk about some of these. Sodium is not corrosive, especially to stainless steel. In fact, it's much less corrosive to steels than water is, as an example, at temperature and pressure. So sodium's great coolant. In fact, going back to the sodium fast reactor, when they decommissioned EBR2, Experimental Breeder Reactor 2 in Idaho, when they cut the pipes off the primary sodium loop, and they had cleaned all the sodium out, obviously, they cut it, they opened it up, you could still see the welder chalk marks inside of the pipe. So sodium is, and you can operate them at atmosphere, another thing I forgot to mention. I mentioned at the beginning, so this one's atmosphere, that one's the previous one is atmosphere. So there actually is some history with lead or lead bismuth cooled reactors. The Russians built 7 Alpha class submarines using lead bismuth. They sunk one of them, they deep sixed one of them, it got plugged up, and reactor didn't run anymore, and they weren't able to retrieve it. It went to the bottom of the ocean. But they also did a couple of onshore prototypes, and so there is some history behind that, just like the sodium-cooled reactors. A lot of the work being done, though, on these reactors is in Europe, including Russia. And you guys can read these bullets as easy as I can. One of the advantages you get, again, if you can see up there, 480 to 800 degrees C. Now, the issue there is that your coolant may not be reactive, but it's very corrosive. So while I said with the sodium, you have this pretty clean coolant, this one, not so much. You got to keep the oxygen control very tight in this. That's just why they plugged up one of their submarine reactors, is because they started forming oxides from the lead, and the bismuth plugged up some of the coolant channels, and they weren't able to get the reactor going. So some advantages here, of course, again, atmosphere, like the sodium-cooled reactors, there's no driving force. And the one thing I did forget to mention is that from a safety standpoint, if you looked at this one and then the previous one, these are both pool-type reactors rather than a loop-type reactor, like light water reactors or water-cooled reactors are, meaning that all the penetrations into the core come from the top. So what that means is that there's no pipe to break off on the side anywhere. So your loss of coolant accident's not credible anymore. Plus, since it's not pressurized, even if you were to cut something off the top, there's no driving force to push the coolant out. So core always stays covered. Gas-cooled fast reactor. So this is one of the ones that has never been built before. It's been conceptualized but never been built. And the idea with this reactor was to take a gas-cooled reactor, put it in the fast spectrum side so you get all the physics advantages of fast reactors, but then this ultra-high temperature you get from a gas-cooled reactor. So the idea is to run this reactor at about 850 degrees Celsius. The challenge you have with this reactor, though, is that at those high temperatures, most metals are out of the question. They just won't survive for any length of time that you'd want them to in a reactor like this. And so one of the things that we looked at for the gas-cooled fast reactor was what kind of materials could we use other than metal in this core. And so I was actually very involved with this project, and we were looking at ceramics, obviously. In this case, we were looking at silicon carbide as one of the lead ceramics, and there were different fuel forms that we were considering, so we had some fabrication R&D that was going on, and then we actually did some irradiations in the Phoenix reactor, which is a test reactor in France, before it shut down, to actually bombard them with neutrons to see how they'd behave under irradiation. So you still have the advantages of the fast reactor. It utilizes uranium much more efficiently, even if you don't reprocess. The high temperature, at that high temperature, even the other ones you can kind of get there, but especially at 850 C, it allows you to get out of just the electricity production side of the house. With that temperature of heat, you can start using it for other processes that are used out in the industry. Of course, a non-reactive coolant, but as I said before, it requires some very advanced materials. So we have the silicon carbide fuel. I actually have some fake fuel that I have sitting on my desk that Oak Ridge made for us, where it looked like the trisol fuel that they use in pebble bed reactors, only it was zirconium carbide clad and silicon carbide clad. And we were looking at ways to do that then to put into, or to be able to use in this kind of a reactor.
What are the form factors for the fuel? You mentioned pebble bed. And
Yeah.
Is that?
Yeah, it's one of the ones that was being considered, but we dropped it after a while just because to make pebbles, especially out of silicon carbide's pretty brittle, and the banging around that would occur, we were afraid would be cracking the pebbles too often. So we had two form factors. One was a more standard pin that you would see in a reactor, only it was a silicon carbide composite clad, which actually is being considered right now in the accident-tolerant fuels program for light water reactors. And then the other one was actually a plate fuel that we were trying to develop, which was a monolithic silicon carbide. And what we looked at was you still took these almost like, it wasn't a trisol particle fuel, but it was built roughly the same way that a trisol particle fuel was. And you'd embed it into a carbon matrix that was very airy, right? It's very porous, right? Lots of voids in it. And you basically make a slurry, and you get this stuff really airy, and so to have these particles distributed, and then you'd infuse silicon into it, and you'd bake it for all intents and purposes. One of the challenges we had was making sure that all the silicon reacted with the carbide to get the silicon carbide matrix to work. There's still some work going on there, but I've since left the lab, and I don't do this work anymore. So there are really those two forms. There's sort of plate fuel, and then this cylindrical, sort of standard-looking fuel. All right, so we've got the first 3 reactors that we looked at, and those are all fast reactors. The next 3 are thermal, with one of them being able to do both a thermal spectrum, neutron spectrum, and a fast spectrum. So I'll talk about those now real quick. Actually, no, I take that back. There's 2 more that can actually be run in a fast spectrum mode because we're actually working on one of them in TerraPower. So this is a very high temperature reactor. Some of you will recognize this as the Next Generation Nuclear Plant, NGNP. This is a program that was hoping to turn into a project with the Department of Energy and some commercial companies to turn into a public-private partnership. There are actually 2 fuel forms that are looked at here. One's called a prismatic fuel. So you think of a hexagonal graphite block with holes in it. Some of the holes you'd put fuel in, which look like little compacts. The other holes were the coolant channels. And you stack these blocks on top of each other. The other one is the standard pebble bed reactor. So graphite pebble, basically, with the same kind of trisol fuel in it. So the idea is to get up to almost 1,000 degrees Celsius. That puts you in another realm with respect to process heat. Again, not so much focused on the electricity side of this, even though at those temperatures you can get fairly high efficiencies out of it. But it turns out there's higher value products that you can get just by using the heat that comes out of the reactor. So designed to be walk-away safe, and I want to talk about that for just a second. This particular reactor and this design, it's not new. We built one similar to that with the prismatic design here in the United States at Fort St. Vrain. Peach Bottom also was a very small version of that. And it had its complications. There was a lot of ingress of water and air into the system, so there were issues with valves and seals. That was one of the main things that they started to look at when they first came out with Gen 4 is, look, we had those issues, so what do? We also looked at the pebble bed reactors that the Germans built, and they did not have these same problems. And of course, it was the valves and the seals. And in fact, the German program had very good fuel. The fuel had better fission product retention than the fuel that we were manufacturing in the U.S. So as far as reactors that have been built before, yes, there have been some similar to this. As far as pebble beds, so the Germans did they built 3 different pebble bed reactors. There is an experimental or test reactor in China right now that's a pebble bed reactor, and they have 2 units that are commercial units that should be finished up again within the next year to 2. It's called HTRPM, and those are in China. So the walk-away safe part. When you think of walk-away safe, what you're really thinking of is, from a reactor standpoint, is If my reactor shuts down, the thing that's different between the reactor and any other power source is I have decay heat that I have to worry about. That decay heat needs to be taken away from the reactor so you don't melt things. With these kinds of reactors, it turns out that doesn't really matter because of the way the fuel is made and what it's encased in, which is all this graphite. You have a huge heat sink that you don't have with other reactors. This heat sink means that you can have everything go wrong with this reactor and it'll sit there and not much will happen, if anything at all. And so there's been a lot of work done to show that that's the case, both at the national labs, universities, and some of the industry folks that are working on this. The walkaway means that you don't want to do anything. You don't want to stick your finger in there. You just want to let it go, because between the physics of the reactor and the high temperature capabilities, specifically the graphite, this huge heat sink, then you don't want to do anything with it. You just want to leave it alone. I'm trying to think. There was one other thing I wanted to say about this. The trisul fuel. So this is very different than fuel that you typically think of in a nuclear reactor. In a nuclear reactor, it's an oxide pellet. It's about this tall. It's about a little bit bigger than a pencil in diameter. But these trisul fuel, it's a teeny particle. And when you start out with a kernel, what we call a kernel, which is either uranium dioxide or uranium oxycarbide, and then you encase that kernel, one with a porous graphite layer. So that's essentially where the gas, any fission gases that might be released end up in there. And then you put a high-density carbonaceous layer on the outside, pyrolytic carbon. So that's sort of the first casing. And then you put a silicon carbide layer outside of that. That's another casing. And then you put another pyrolytic carbon layer outside of that. And so these little kernels act as little pressure vessels. And so even if one fails, because it's so small, the amount of radionuclides that are in there that may come out, turns out you might not even see them, because they're just so small. You have to have multiple failures of all these particles. And that's from a statistic standpoint, that just doesn't happen. So it's a very different kind of fuel than what's used in current reactors. The previous ones that I showed with the lead, bismuth, the sodium cooled, and even the gas cooled, the gas cooled, we were looking also at these little particles. So a couple of them are a little bit different. But it's a different kind of fuel and a different kind of mentality about, okay, what are we doing? Well, what we're doing is we're making the fuel extremely robust and put it in a system that can absorb all this heat so that if you do have something that goes wrong, there's not a problem. All right, so the final couple of ones, this is a supercritical water-cooled reactor. This one and the next one, the molten salt-cooled reactor or molten salt reactor, both can be operated in a fast spectrum mode. So they can either be thermal or fast spectrum. And the reason you can do this with this water-cooled reactor here is because of the density of the water. And it's water at the supercritical point, meaning that there's no phase change. There's just a density change in the coolant. That's it. The reason that this one's attractive, and no one's ever built, this is the second one that there's no reactor that's ever been built on this. But this one's attractive because right now, if you look at a lot of the coal plants, especially the newer coal plants, they operate on supercritical water cycles. And the reason being is because you get extremely high efficiencies out of this, extremely high efficiencies. So what are the challenges then? So we get high efficiencies, we get to use both technology on the balance of plant side that comes from the coal side of the house, and we can use light water reactor technology in some sense. Well, when you get to the critical point of water, even before that, you're extremely high pressures and temperatures. Water tends to be very corrosive at those conditions. You can just ask the coal guys who run their supercritical plants. There's a lot of stuff they have to replace all the time. So how do we deal with that? That's what we were looking at, water chemistry and the materials. Turns out to be a very big issue, and how we get there. One of the other challenges with the supercritical water-cooled reactor, though, is that because of the thermodynamics of the reactor and the enthalpy rise across the core, you really have to be careful about how you operate this plant. In some sense, you're kind of on this tipping point because of how you're operating it. So there's been I would say a lot of work done at the beginning of this plant, but many of the countries and companies that were involved in it shied away at some point just because of the challenges. It doesn't mean it can't be done. It just means they thought it was a little bit farther out than what they were willing to invest in.
Kevin, can I just interrupt you for a
Sure.
second? You know, we talked about this kind of consortium of 10, now 12 countries, their kind of cooperation, even through treaty agreements,
Yeah.
to pursue or cooperatively pursue these given technologies. Is there a methodology in that process where something like this, maybe they all agree, we're dropping this one going forward, or it's not as viable as we thought it was? I mean, is there a continuing, ongoing review process of this?
There's not an ongoing review process. However, the way it works is that the countries will just stop working on it. So it stays in the Gen 4. Instead of taking it out, it stays in there because countries like, I'll give you an example, a country like Canada, you know, they're really invested in the water side and specifically the heavy water side. They actually have a version of this that uses heavy water. So I guess the one thing I should have said in the beginning is that there are permutations on these 6 systems, right? It's still supercritical, et cetera, et cetera. And I'll talk, at the end of my talk, I'll talk about TerraPower, the 2 that we've been working on. They are permutations of what we've seen here. So Canada is still very interested in this. They are, and I think Switzerland are still doing some work. But you'll see, and this was the whole idea from the beginning, is if you put the 6 systems out there, then countries will start to align, countries/companies will start to align, and you'll come to some consensus at some point. And you have seen that. The exceptions would be there's a couple where there's maybe 1 or 2 countries still doing work. And even the ones that they're not, they've left them on the table. And so the next one, in fact, I'll specifically talk about this one because at the beginning, this one kind of, it had some interest, but was almost left on the table at some point. But now in the United States, it turns out this has become much more interesting as of late. And we have some companies, including ours, that are looking at versions of this, okay? So the molten salt reactor, so there's 2 types. The first type is where the fuel is solid and you simply use the salt to cool it. So think of the very high temperature reactor. Instead of using gas, you use a molten salt as the coolant. What that allows you to do is you can actually operate at higher power densities and still maintain the safety aspects. Higher power density means from a cost standpoint, you recover it a lot faster. It's more economical if you'd like to think of it from that standpoint. The second version, which is the one that's the one that most people think of when they think of molten salt reactor, is the fuel is actually dissolved in the salt itself. So this is a liquid-fueled reactor. It poses a whole bunch of different technical challenges that you need to think on. One is online waste management. This is the other reactor you can operate either as a thermal reactor or as a fast reactor. If you operate as a thermal reactor, you can see the second major bullet, you have to manage the waste in it. When the fission products start to build up, they act as a neutron poison and it shuts the reactor down eventually. If you're running this around as a salt, the idea is that you could continuously run it with the exception of certain shutdown periods to do maintenance on certain items, pumps and other things within the plant. But you can run it for much longer, so your capacity factors would be much higher than even current plants. But if you do that, you've got to do something with the fission products that get into the salt. And so the molten salt reactor experiment at Oak Ridge, they had this whole, in fact, their cleanup system was bigger than the reactor itself. The reactor was probably, yay big around. The cleanup system were a couple of big buildings off to the side. Problematic. And you could also think that if you don't design it right, this could be a potential problem from a proliferation standpoint because the the fuel's already dissolved. You don't have to dissolve the fuel. With solid fuel, you got to at least do that step first. But if you do it right, if you design it right, you can at least in some sense pull that back a little bit. Let's see. Technical focus. The big one here in salt, whether it's a solid fueled or the salt's in, either way, it's a chemistry problem, right? Because one of the things you're trading off here is that in reactors, the neutrons do damage to the materials. If you don't have anything that the fuel's encased in, like for the liquid salt, liquid fueled version, then really the structures on the outside don't see much of the neutrons. They're all concentrated where the salt is. There's not a structural material issue from the radiation standpoint. But think of it this way. When you fission, you're creating the periodic table. right? I mean, you have two humps where there's a much greater quantity of those elements on those two humps, but overall you're creating the periodic table. If I have a salt and I want this salt to behave a certain way with regard to corrosion, erosion, etc., if I'm creating the periodic table in it from a chemistry standpoint, you've got all kinds of oxidation states you have to worry about. It's a chemist's either dream or nightmare, depending how you look at it. Okay. So I got about 5 minutes left, and so let me talk about real quick. This is, by the way, this is the last slide. Let me talk a little bit about not so much what this graph says, but what we're doing in TerraPower. So this is kind of generic to pretty much anyone who's looking at new designs of anything, for that matter. And so in TerraPower, what we did was we looked at the different Gen 4 designs and including other designs that we thought of before and said, okay, so if we want to supply on a very large scale power to the masses, then what's the best way to do it? Like I said in the beginning, obviously we landed on nuclear as one of the ways. It's not the only way, but it's one of the ways. And it has a history of scaling up very quickly. If you take France, they were roughly 2 to 3% in the 1970s nuclear. In less than, I don't think it was 20 years, I think it was about 10 years, 10 to 15 years, they went from 2 to 3% to 80% nuclear, right? So that, and you got to think of it this way, it's not just the reactor, it's all the stuff that goes with it, all the concrete, all the steel, everything. And they were able to ramp that up very quickly. And so they replaced essentially all of their fossil sources with the nuclear source. And so we landed on nuclear, and the two designs that we thought would best meet what our goals were, we have the Gen 4 goals, and we've emphasized some more than others, is a sodium-cooled fast reactor called the traveling wave reactor. The difference between that and what I showed before is most sodium-cooled fast reactors, in fact all of them, talk about or rely on reprocessing the fuel, meaning once the fuel's been in the reactor, you take it out, you reprocess it, you extract the fissile material, you make new fuel, you put that back in. What that does is instead of having to enrich uranium, you're using the fissile material that's being created out of the uranium that's in that you put in the first place. And eventually, in fact, even after the first load, even in reprocessing, the only input then to the reactor is uranium, not enriched uranium. So if you think of it this way, there are hundreds of thousands of metric tons of depleted uranium sitting around the world, and right now it leaches into the ground. I mean, it's a waste. And the idea is the fast reactors will use that. But we thought, well, what if the thought that we had is, can we do that without having to reprocess? Because reprocessing, frankly, does bring a bunch of proliferation concerns. If you think of proliferation, there are really 2 points that you worry about. The first point is enrichment, right? Because you don't need a reactor to make a nuclear weapon. You just need to be able to enrich the uranium to do that. That's how we made our first one, okay? And that's how many other countries did. The second point is that if you put uranium in there and convert it to plutonium, or thorium in there and convert it into uranium-233, you need to reprocess it. Those are the 2 points of proliferation. So what if we said, let's take away the one, the reprocessing one, and what if we shrink this other one down and we say, we now have a system that we don't need to build any more enrichment plants because enrichment capacity around the world is suffice for these plants that exist right now. So if anyone does start to build an enrichment plant, you have to ask why. If you don't need it, there's plenty of enrichment plants and you don't need it, then why would you build it? So the idea is to pull back that proliferation side. And so what we did was we have been designing a sodium fast reactor that actually the fissile material that's created in the fuel, we use it in situ. What that means is that the fuel then that builds up the fissile material gets put into the center of the core eventually, and it becomes the fissile driver, if you wish. We still have input into it, and the ideal is that you have all the input you need for the life of the plant, so it never gets opened up.
It's a closed loop, but it's closed loop within the reactor.
Within the reactor itself. All that happens is some fuel movement in the core, not out or into or out of the core. That's the idea. So that's the traveling wave reactor. And the actual name traveling wave comes from, because from a physics standpoint, if you do what we're talking about and you just put depleted or natural uranium on the outside of the core or in front of where the original fissile material that you charged it with, then there is essentially two waves, solitons, that move across the fuel. The first one is called a breeding wave, turns the fertile into fissile material, and then the burning wave follows closely right behind it. Okay? That's why it's called traveling wave. Now there's a second one that we worked on, so that's a sodium fast reactor. The second one that we're currently working on right now, and in fact we're working with Southern Company, EPRI, Vanderbilt University, and Oak Ridge National Lab, and it's called a molten chloride fast reactor. So it's a very specific kind of salt that behaves very well for a fast reactor, meaning we maintain the neutrons in the fission spectrum, so roughly average 2 MeV energy neutrons. So in essence, it looks like the traveling wave reactor only in liquid fuel form. That's kind of how you'd have to look at it, or how you can look at it. The advantage you have by going to a fast reactor with the molten salt reactor is that whole processing part that I told you about, like they had to do with the MSRE at Oak Ridge. You don't need that, because fast reactors, the fission products don't act as poisons like they do in a thermal reactor. You can run them much longer. You can build up a lot of fission products, and it doesn't affect the physics of the reactor, or very little. So those are the two reactors that we're working on, and we went through this process here to develop these reactors, and hopefully, of course, the idea is that with all the experimental work and the work we're doing with the other companies, countries, and national labs, that we'll be able to deploy these reactors relatively quickly, like within the next 10 to 20 years. And I'll end with saying that's quick, especially when you look at, take an example, Boeing and the 787. If you look at their time frame for that, we're on that same order as far as timing is concerned. And with that, I will finish, and I'll open it up to questions.
Thank you, Kevan. I get the benefit of always having the first question, at least when I'm the host tonight. I find all this fascinating, of course, but then I understand nuclear energy and nuclear power. Could you give us a rundown, and even I realize we're taping this, of what you would consider the top 2 or 3 players in the Gen 4 field in the U.S., and which particular design approaches each of them following, like yourself, NuScale, maybe General Atomic? I mean,
Yeah.
who you think I hate to say the real players, but the most aggressive, advanced, prominent players, and which of the given ones they're looking at?
Yeah, I would say that there's probably a group, and I want to be careful because I don't want to make them all mad, but I really think there's a group of about 10 that are real serious. And when I say serious, I'm talking about, it's one thing to sit at your computer, because now we have the computational capability, right? We have supercomputers, in fact, that we can lease time on, and we can do these really awesome simulations. Even computational fluid dynamics, we can couple with these, and things that used to take months and months and months to get answers to, we can get them to in a week or a few days if we want. Much different. Those are paper studies, though, because what happens is that it's great to do it on the computer. And by the way, my technical background, when I worked at the lab, I was a reactor physicist. I did paper reactors. That's what I did. And what I realized as I started leading different projects was that where the rubber meets the road is in material, and there's other things, but materials is really where the rubber meets the road, because when you go to higher temperatures, you use different coolants, the materials are set, and you can make a new material, but it takes almost a decade to get that material out. Code-wise, everything, right? And so the companies, so I'm not going to name them, but what I am going to do is if you watch the companies that are doing real material work, and I'm not saying just the materials, but like building pumps and testing them, building valves, irradiating materials. Those are the companies that are doing more than just paper studies. And those are the companies you should watch out for. And of course, I should say, obviously we are. The thing I didn't say was, as part of our testing, as an example, we're even doing irradiations. We have advanced fuels in the advanced test reactor in Idaho right now. We have materials in the fast reactor in Russia being irradiated right now. And those are expensive prospects, by the way. They take a while, and they're expensive. So I know I didn't completely answer your question, because I'm not going to name names, but it's the ones who are doing more than just the paper stuff.
Once I get a beer or 6 in you, I'll ask the question again.
Dr. Weaver, you said you expect to deploy in, all things considered, 10 to 20 years, but your initial slides had a 2040 target date for the population and electricity demand growth. And so there's a bit of a disconnect there. If it's going to be, 10 to 20 years out, you're not going to have much time to scale to have much of a bite out of that needed target. So
I think it depends on how you deploy it though, right? So that when you talk 10 to 20 years, that's when you start deploying it. Yes, it's not as fast as I think we would like. I agree. But I'll go back and I'll use the example with France, is that it may take 10 to 20 years, but it can scale quickly after that. Meaning that if between 10 and 15 years, if I can go from 2% to 80%, I think it's a pretty good case to show that if you can get that first reactor going, and that's really what it is, by the way. You get the first one going to show people that it works, the rest of it takes off.
Okay, can you follow up this question? Can I follow up this question? I just read the newspaper from China saying that the first, traveling wave reactor, they just signed the contractor with some of the company in China and it will be built. Can you give me some update on that front?
Sure, I'd be happy to. The answer, well, first of all, let me correct something. There wasn't a contract. It's not a contract, meaning, we're not going to build it right now because there's still some more work that has to be done. But what did happen in China, we've been working with the Chinese for quite a while. When I talked in the beginning, the industrialized countries have growth rates that are single digit, even maybe even sub-single digit. They don't even small modular reactors are a little bit difficult in that kind of an environment. China, on the other hand, is on the steep part of the curve. They're in double-digit growth territory right now. And so as a private company, we are looking and had been looking towards an entity, in this case a country, that had a need that could help move it from where it is now to where we're actually producing electricity. Then it moves out to the other places with the partner at that time. In this case, it would be the Chinese. And so what you saw was a few weeks ago, there was a group of companies. I mean, this is all in the media, right? A group of companies in China, Shenhua, which is like mostly coal, Chinese National Nuclear Corporation, and a few others that formed a company that then will be part of the joint venture. And then on October 2nd is when the initial documents for the joint venture were signed, if that makes sense. So TerraPower, Chinese National Nuclear Corporation, Shenhua, and I don't remember the other three companies. I apologize. Yes, they did sign documents to start the formation of a joint venture. So that's what you read. But to sort of take it the next step, the answer is that's how you start the process, right? And you get there. So the idea is that the first prototype will probably be built in China, the way things are going.
Let me do a quick follow-up on that one. So does that mean you don't have much chance of success in the U.S.?
No, that's not what it means. What it means is that the market for the time being is not, the market's better in China than it is in the U.S. And as a private company, we owe it to our investors and our shareholders to make sure we go to the right markets. What I'll say to follow up with that is if the policies are right and if the timing will probably work out right too, is if you look at the current fleet of reactors in the United States, about the 2040 timeframe, those are going to drop off. They're going to be decommissioned. But we'll have already had, if you look at our timeframe, we'll have already built the first prototype and several commercial versions in China, and then the idea would be to come back and start replacing the plants that are going to be decommissioned.
So Dr. Beach kind of took most of my question, but as far as development in the U.S. is concerned,
Yeah.
We in here know that these are not the same reactors as as the ones that are already built.
Yeah.
But most people don't understand that. If it's nuclear, and we don't want it. Do you see that not happening in the U.S.? I mean, I understand that we are going to have a need when these reactors get retired, but
Yeah.
is that not going to be feasible in the U.S. and we're going to count on the rest of the world being more flexible in adopting this?
No, I think that in the United States, even though the environment right now for nuclear isn't that great, I would say that if you want to call it the public opinion side of it, it's still not as great as we'd like to see it, but it turns out that's not the problem. The problem is the economics side of it, right? That's the real problem, is that these reactors, you can put them in what's called the mega project side, right? And when I talk about mega projects, I'm talking about projects that can take up to 10 years or more to build, number one. And number two are billions of dollars, not hundreds of millions, but billions of dollars, right? So the capital expenditure is very high. That part is really what the big challenge is with nuclear right now, is how do we get it out of the mega project into something that's more doable? The public perception is going to be what it is. I'm not discounting it, by the way, don't get me wrong. But it's not that bad. If you take into account emissions, and global warming is somewhat of a debated hot topic, but if you just look at emissions, so I'll give you an example. So the times that I've been to Beijing, all the times I've been to Beijing, I think there's twice when I actually see the mountains outside of the city. Other than that, I couldn't even see 2 blocks, right? So forget about global warming. Let's talk about the real health issue of the emissions, right? I mean, it kills a couple million people a year. I think it's 1.2 million roughly in China each year die because of emissions, right? Respiratory illness. So I think from the standpoint of clean and then talking about everyone's worried about the safety, I think we'll get there. It's the economics that's the big issue, is how do we get it so that it really does make sense from an economic standpoint and we can actually really compete on an economic basis with the other power sources. Does that make sense?
So given that these designs are quite different than the PWRs and BWRs that exist currently, could you speak a little bit about the licensing process and how quickly or slowly you see that moving forward, and if there's like a particular design aspect that may be a stumbling block, or if it just...
So let me use the U.S. as the first example. In the United States, the regulatory framework and the way it's set up right now really is much more catered towards, in fact, it's all catered towards light water reactors, right? There used to be a time when there were people in the NRC who did have expertise outside of that, but that was a long time ago, and I know a lot of them, and a lot of them are retired, and they're gone. So the issue is not so much timing, meaning that it just takes a long time, but the issue is that what's the timing with regard to get everyone up to speed on these new, right? These new plans. Think of it this way. So although the FAA is typically a little bit easier when it comes to regulation, if you came up with some crazy new type of aircraft, I mean seriously different than what's being built now, would the FAA be ready to, at that point, right when you gave them the design, to be able to do it? And the answer is of course not. They would have to come up to speed and understand. So that's one of the things we have, that's a challenge that we're dealing with. So to answer your question, there's been, over the past probably 3-4 years, if not longer, there has been a real effort between the Department of Energy and the NRC to start looking at this. And there's been various meetings, and there's, in fact, there was a document called the General Design Criteria, which you can find in NRC documents, and they're rewriting it for non-light water reactors. So there is progress going on. But it takes a while. I think the next question you have, well, what about outside of the U.S.? Well, the advantage that some of the other countries have is some of them have already licensed non-light water reactors, Russia being one of them, France being another one, the China being another one. So other countries actually have licensed non-light water reactors. Okay.
So, do you have a bridge analysis that looks at, say, here's a $25 billion unfinished reactor in the U.S., that's what it seems to be cost of, and then how you change substantially, radically, the cost profile to make the economics pencil out, so we could see a bridge, because the race here is renewables plus storage.
Yeah,
Right,
yeah.
against this
Yeah.
nuclear power. And so to create a vision that shows how it's going to be competitive from an economic standpoint. And secondly, that may relate to that, so you can get some technology. It seems like our Navy is just happy campers with existing technology. They're not going to drive the technology. Are there other militaries that want to go nuclear as far as their Navy that could drive some of these new generation reactors to really drive the prototyping and testing forward?
I would say that the Russians kind of got there with their Alpha class submarines, the lead bismuth cooled ones, but they found that it was still better to use just water in those. And part of it is just the physics and the resulting equipment that you have to put around it. You get to some point, just like you said, where you're comfortable. I would point out though that the Navy's satisfied, but what they're satisfied with is using water as a coolant. That's what they're satisfied with. When you look at their designs, they have changed designs pretty radically over the last 2 decades, to the point now where the new boats and ships that are coming out have lifetime cores in them. They used to go into Bremerton in the Puget Sound and over to the East Coast, cut a big old hole in the hull, pull the reactor out and put a new one in and weld everything back up. And they don't do that anymore. All the new boats and ships are lifetime cores. That's a big change. There's a core design change, a fuel change. So I would say that it's true that it's still light water reactor technology, so it doesn't drive the other thing. But I'm going to be careful here. But I do know that the Navy has been looking at alternate coolants. I won't specify which ones, but they have. The problem is that when you say Navy drive it, the military likes to keep that stuff close until it's very well developed, and then they feel like they're on to the next 3rd or 4th generation one, and then they'll give that rest of that technology to the civilian world. So that's a problem. So by the time we see their non-light water coolant stuff come out, they'll have been using it for years, and it's going to be several decades before we see that, unless we develop ourselves on the civilian side, if that answers your question. And to answer the question, the first part of it on the economics, so I was fortunate enough that I got asked to be on one of the panels for the MIT report, Future of Nuclear Power. And the one I was on was specifically the economics. That's a hard question. And what I don't want to steal the thunder, because the report itself will be coming out sometime next year. But I will tell you what we found on that panel was that it's not the nuclear steam supply system that's the problem. That's not where the cost is. It's all the indirect. So it's all the civil engineering, and it's all the interest that's accrued. It's basically the concrete and stuff it's going to cost what it costs, but it turns out the indirect costs. And if you don't have a finished design, which we never do, that's what drives up your cost right there. So it's all the indirect. And we got to figure out how to get past that. And I would say that just by being on that panel, I think one of the things that we need to really, really consider is let's finish the design, complete the design first before we go and build it, rather than go to preliminary and then do the final design when you're pouring concrete. When you say, oh crud, I got to go back now and I have to break up all this concrete and pour another slab over here because we have to make a change. And you'd be surprised at how often that happens. But by the way, I want to add in there this mega project and that particular piece, that's not unique to nuclear, by the way. One of the examples they brought up in that panel was anything that's mega project, if you look from a world view, 80% of them are behind schedule and over budget. 80%, and that's not just nuclear, that's all big projects, like big dam projects. Or in the case that the one that they showed was a refinery that they're building in Qatar. Right? Initial price tag, $5 billion. Final price tag, $24 billion. That was for a refinery. So it's not just a nuclear problem. And it turns out it was those indirects. They had to go back and make changes. So anyway.
You know, that's a good answer, and that's one that somehow we need to find a symposium speaker on. I mean, you think about the big dig in Boston. I mean, you just go down the list of these super big civil engineering industrial projects that globally, it's almost like we don't know how to do it anymore, or we just can't estimate the pricing of program management. You all should probably go learn how to be program managers. Maybe that's the real future of what we need in the world. Was there one more question?
Oh, okay, I'm back. Just to jump on recent news, I guess the DOE has proposed to FERC that there might be some mechanism they could look at for what do they call it, like basically getting money back to power plants that can keep fuel on site, being able to subsidize power plants. Would that affect nuclear? Would you support some sort of rulemaking like that? And does that change the economics in the long term?
So first of all, I think what you're referring to is the fact that Yucca Mountain's not open, and so they don't have anything else to do with that. And so, and you correct me if I'm wrong, because what happened was the DOE's given them money back because the DOE promised to take that fuel
So
decades ago.
when I said giving money back, I was wrong. So I believe they're basically looking for some mechanism to pay power plants, or like there's got to be some mechanism for power plants to get paid for holding fuel on site, which would seem to basically refer to just coal or potentially nuclear.
You mean the spent fuel, correct?
No, he's talking about power plant reliability and a current DOE potential initiative with FERC to incentivize or greater value coal
sorry.
power plants
Sorry.
and potentially nuclear plants because you have on-site fuel and their greater reliability sustained.
Yes, yeah. Okay, yeah, totally different question than what I thought it was. Thank you for clarifying. I support that, but only in that it levels the playing field. Because if you look, and I want to be careful here, because like I said, we need all kinds of power sources, especially those who don't emit. So wind and solar as an example, right? But when you don't level the playing field and you favor one over the other, which by the way, that does happen. I'll give you an example. So my dad was telling me that in southeast Idaho, the way it's set up, and I think this is not atypical, I think this is typical, is that when the wind is running, you have to buy it. That happens in Washington. That I do know for sure. The utilities have to buy that wind power. So regardless of how much it costs, by the way, regardless of how much it costs, you have to buy it. Now, fortunately, it's not that expensive. But the problem occurs is when you do that, you skew the market, because then that wind power, on an average basis, only operates 33% of the time. The solar, 25%, solar voltaic, I have to be careful, right? 25% of the time. And up to now, when I showed that the first slide, when I said it's scaling, we don't make enough batteries in the world to go to that, to 100 terawatts. I mean, we're so far. We don't even have enough to do what we've got now, let alone what we're talking about there. So I am all for putting money into storage, by the way, to figure out how to solve that problem, because it will really help on the renewables side, really help. But if you force the utilities to go and buy something that doesn't make economic sense, then it skews the market, and those power plants that are on the reliability side very high, if you have to shut them down because you got to go buy this, then it skews the market. If you understand what I'm saying? And by the way, let me point out too that on the renewable side, I think what a lot of people forget is that for every megawatt of renewable that is built, there's 0.9 megawatts of fossil that are backing it up. And you typically have to build that. And right now it's natural gas. So I went to Jim Conca and I asked him about this. And I said, what is that number? And that's the number he came up with. So what that means is that for every and let's say we normalize this so that 1 is 1 megawatt, figure out what you want. If I do 1 in solar or 1 in wind, then what I have to do is I have to build 0.9 of fossil to back, because that's what they do, because gas is really cheap right now. So you have to start asking yourself the question, if my windmills and my solar, at least for right now, are only running at 33 and 25% capacity, then the other 2/3 or 3/4 of the time I'm spitting CO2 in the air, right? So how am I actually helping the problem? Well, yeah, I've incrementally, very small, helped it. But if then I'm forced, to have to buy that, and then I got to jump back. If you talk to the utilities, it's a real pain in the keister to have to jump back and forth, and that's what you end up having to do. So I'm torn a little bit here, because I think the high capacity factor energy sources need to be given a fair shake. But I want to be careful. You got to be careful, because you might skew it the other way. I guess that's what I'm getting at, is it's skewed one way, and you don't want to skew it clear towards the other side either, right? Because I can tell you right now, if utilities had if you ask them, if they had their druthers, and you took them and gave them a bunch of beer and asked them to tell the truth, right? This is what they would say. Forget about all these others. I just want to build natural gas-fired power plants. That's what they would say, because it's cheap, they're quick to build, they don't cost much to build, and natural gas is cheap right now. And so they would, all of them, nuclear would be out of the question, wind would be out of the question, solar, so they would get rid of all of it. So anyway.
I don't know if we want to go there, Kerry.
Yeah.
Well, you're getting in a whole nother range.
I know.
I
I just,
talk about.
Well,
yeah,
yeah,
I just
that
say that because the
opened up
utility
the
guys that
box.
we know,
And it depends on the market you're in.
it does. I agree.
Well, that was going to be part of my question is, when you say the market, what do you mean? Most times when people or economists set up markets, they're by definition based on marginal costs, not total costs. That's kind of roughly how we interpret capitalism and markets in general. So that was before wind or solar or nuclear. The other question, a little poke at maybe Jim Conca rather than yourself, but let's say I had no wind or solar and I have a bunch of thermal power plants. How much of the thermal power plants are backing up wind and solar?
Now say that again.
Let's say I'm ERCOT, Texas 20 years ago, I have no wind or solar, and then I install one wind turbine. How much of the grid is backing up the one wind turbine? How many plants did I install to back up the wind turbine?
At that point, you haven't done any, right?
Actually, at this point, we haven't done any.
Yeah, you haven't done
And
any.
we're at extremely high penetration levels, so it really depends on the market you're in. It
Correct.
depends on the region you're in. It depends on what existing generation capacity you had
Yeah.
and what the portfolio looked like. And the answer is it depends.
Yeah. Well, yeah, because that brings me to the question, right? Is it additional capacity or is it simply capacity you put in because it makes economic sense to go there,
We
right?
have a lot of peaking capacity in Texas
Yeah.
because we have very hot summers long before we ever thought about wind or solar. So
Yeah.
we already had the built-in
Exactly,
backup
exactly.
capacity. So it was
Yeah.
a very synergistic thing.
Yeah, you're right. And right, the market, it depends, right? Because in the Northwest, yeah, solar doesn't make sense. I mean, seriously, 9 months out of the year, we don't even see the sun. And I'm not kidding, by the way, you guys. By the way, the summers are great. If you ever get too hot, August is an awesome place to be in Seattle. It is sunny, but it never gets above about 80, 85. But during the wintertime, yeah, starting basically October right now, by the end of this month, it'll be cloudy, and we won't see the sun maybe a couple, 3 times between now and June.
And
Basically.
that's why hydropower is so great up
Hydropower is great, yes.
there. Okay.
All right.
Thank you very much, Kevin.
Thanks.